The whispers of a simpler life. Close your eyes for a moment and simply listen. What do you hear? In today's fast, constantly connected world, many of us have grown used to the low hum of electricity, the endless ping of phone alerts, and the quiet pressure of bills that never seem to stop arriving. We are repeatedly told that building a good life, or even a productive small farm, requires the latest equipment, thick concrete foundations, and expensive prefabricated systems that can keep us tied to monthly payments for years. But here is a question worth asking. Are we really building the life we want, or are we paying to remain dependent on systems we cannot control? And when did complicated become another word for strong? Travel the back roads of Lancaster County, Pennsylvania, or Holmes County, Ohio, and you will meet people who chose a different path generations ago. The Amish have built productive, self-reliant farms without depending on roaring diesel machinery, the public electrical grid, or heavy long-term debt. Yet their homes, poultry houses, livestock shelters, and enormous barns continue to stand straight and solid through bitter winters, violent winds, heavy snow, and punishing summer heat. Many of these buildings remain useful far longer than modern structures raised with advanced tools and powerful machines. So what is their secret? It is not about exhausting the body with harder labor. It is about using experience to build more intelligently. It means understanding how wood expands and contracts, how weight travels through a frame, how gravity can reduce daily labor, and how a skilled community can accomplish what one person cannot do alone. Today on Farmyard Care, we are opening the door to that practical building knowledge. We will explore 12 simple but remarkably effective Amish building principles that can be applied to a small farm, a backyard homestead, a livestock area, or a working garden. Each one offers a way to reduce waste, improve durability, and create structures that serve both people and animals for years. This is more than a lesson about boards, posts, and joints. It is a step toward greater independence, built one careful decision at a time. So let the noise of modern life fade into the background, and let's discover how thoughtful design, natural forces, and the land itself can do more of the heavy work. Tip 1. Skid-mounted elevation and ground isolation. Let's begin at the lowest point of any farm structure, because this is where a building either gains lasting strength or begins a slow decline. Tip number 1 is skid-mounted elevation and ground isolation. When many homesteaders plan a tool shed, movable chicken coop, feed room, or small workshop, they immediately think about pouring a concrete foundation or placing the wooden frame directly on the lawn. Experienced Amish builders follow a much simpler rule. Once untreated wood remains in contact with damp soil, decay has already begun. Moisture rises from the ground, enters the wood fibers, and gradually weakens the floor frame until doors shift, floors sag, and the entire structure loses stability. Their solution is both practical and durable. Smaller buildings that may need to be moved are constructed on heavy wooden skids. These are usually thick, rough-sawn timbers measuring about 4 by 7 inches, or roughly 7 inches in height, often made from larch or hemlock. These species are chosen for a reason. Their natural resins give them better resistance to moisture, fungal decay, and certain wood-boring insects than many softer, less durable woods. On a working farm where rain, mud, manure moisture, and changing weather are constant concerns, selecting the right timber at ground level can add years to the useful life of a structure. Raising the floor frame about 7 inches above the ground achieves 2 important results. First, it interrupts the movement of soil moisture into the floor joists. Second, it creates an open air space beneath the building. Air can travel underneath, carrying away dampness and helping the wood dry faster after heavy rain. This ventilation gap is especially valuable beneath poultry houses and livestock shelters. Moisture trapped under a floor encourages mold, odors, insects, and premature rot. A dry underside protects both the structure and the animals living above it. The skids also spread the building's weight across a wider area. The structure remains stable, self-supporting, and movable. If the farm layout changes, the shed or coop can be pulled to a new location with a tractor or truck instead of leaving behind an unused concrete slab. It is worth asking how much flexibility we lose when every small farm building is permanently fixed to one piece of ground. Tip 2. Gradient compensating foundation pads. Even the strongest wooden skids need a firm and level surface beneath them. This brings us to tip number 2. Gradient compensating foundation pads. One of the most common mistakes made by new builders is placing a shed, coop, or animal shelter directly on uneven grass. The soft topsoil compresses differently under each part of the building. Over time, one corner begins to sink, the floor frame twists, doors become difficult to close, siding starts to buckle, and the roofline may slowly sag. The Amish method of preparing a site is straightforward and far less expensive than pouring a full concrete foundation. The first step is to study the slope of the ground. On a relatively level site with less than 6 inches of variation, the grass, roots, and soft organic topsoil are removed. These materials hold moisture and compress too easily to support a building reliably. The cleared area is then filled with crushed limestone or coarse gravel and compacted into a solid pad. The surface should be slightly raised toward the center or shaped so water cannot collect beneath the building. The gravel pad should also extend at least 12 inches beyond every side of the structure. This detail may seem minor, but it makes a major difference during storms. Water falling from the roof lands on the gravel rather than splashing mud and moisture against the wooden siding. The coarse stone allows rainwater to drain away quickly instead of pooling around the base. On gently sloping ground with less than about 8 inches of difference, precast concrete patio blocks can be placed beneath the treated skids. Spacing them roughly every 4 feet provides regular support and helps keep the floor level. A steeper slope requires a different approach. When the ground drops more than a foot, the Amish commonly move to a post and beam foundation. Vertical posts are set deeply and supported on properly sized concrete footing pads so that the structure can remain level even though the land beneath it is not. The key lesson is to work with the shape of the land rather than trying to overpower it with unnecessary excavation and concrete. A carefully prepared foundation pad protects the frame, improves drainage, keeps doors operating properly, and gives the entire building a much longer working life. Tip 3. Moisture impervious subsill masonry. Larger two-level structures, especially livestock barns built into hillsides, face a different set of challenges. This brings us to tip number 3, moisture impervious subsill masonry. Traditional bank barns are partly built into a slope. Their lower walls may remain in contact with damp soil, surface runoff, and the humid conditions created by cattle, horses, bedding, and manure. If these lower walls were framed entirely with timber, the constant exposure to moisture could severely weaken the wood within a relatively short time. To avoid this problem, Amish builders often construct the lower level from stone masonry or concrete block. These materials tolerate ground contact and barn moisture far better than ordinary wood framing. However, building the wall is only part of the process. After the blocks or stones are laid, the mortar must be allowed to cure properly before the heavy timber frame is placed above it. This usually means waiting at least a week and sometimes longer, depending on the conditions. Mortar needs time to develop sufficient compressive strength. If massive beams are loaded onto fresh masonry too soon, the joints may compress unevenly. That can create weak points, cracking, or movement beneath the weight of the upper barn. Using masonry at the lower level provides several practical advantages in livestock buildings. Termites and powder post beetles have no exposed structural wood to attack at ground level. Solid block or stone walls also withstand the pressure of cattle leaning against them and the impact of horses kicking or rubbing along the surface. Sanitation is another major benefit. Livestock areas must be cleaned regularly to control manure buildup, parasites, moisture, odors, and disease. Concrete block and stone can be scrubbed, rinsed, and treated with appropriate barn cleaning or lime washing practices far more easily than exposed wooden walls. This is particularly useful around dairy stalls, feeding areas, wash zones, and other places where clean surfaces directly affect animal health and product quality. The principle is simple. Use timber where it can remain dry, and use masonry where the building meets damp earth, livestock pressure, and repeated cleaning. Good construction is not about forcing one material to perform every job. It is about placing each material where its natural strengths are most useful. Tip 4. Passive solar and compost thermal vectors. Now let's look at ways to keep growing areas and livestock shelters warmer without depending entirely on electricity, propane, or natural gas. Tip number 4 is passive solar and compost thermal vectors. Many modern greenhouses and animal shelters rely on electric heat lamps, propane heaters, and powered ventilation equipment. These systems can be costly to operate and may stop working during a winter power outage. Amish builders instead look for ways to use sunlight, biological activity, and stored heat before adding mechanical equipment. The first step is orientation. Greenhouses and suitable livestock shelters are positioned to receive strong southern sunlight. During winter, the sun remains lower in the sky, allowing its rays to enter deeply through south-facing windows or glazing. That sunlight warms the interior air, floors, walls, soil, and bedding without consuming fuel. In livestock buildings, passive solar gain can help reduce cold stress when it is combined with dry bedding, controlled drafts, and proper ventilation. Another useful source of warmth comes from active compost. When manure, straw, leaves, and other organic materials decompose under suitable moisture and aeration, billions of microorganisms break them down. Their biological activity releases heat. By placing an active compost bed beneath or beside a growing area, that heat can warm the surrounding soil. It rises slowly and helps stabilize the temperature around plant roots, even when the air above becomes cold. On a farm, manure provides a valuable compost ingredient, but it must be managed carefully. The pile needs the right balance of carbon-rich material, moisture, oxygen, and volume. Poorly managed manure can create excess ammonia, harmful gases, odors, or fire risk, so it should not simply be piled inside a closed animal shelter. To hold more daytime warmth, heavy thermal materials can be placed inside the structure. Dark water barrels, stone paths, masonry walls, and gravel floors absorb solar heat during the day. After sunset, they release that stored energy gradually as the air cools. Each element supports the others. Sunlight supplies free energy. Thermal mass stores it. Compost activity contributes steady biological heat and eventually produces valuable soil amendment. This does not mean every cold climate can avoid supplemental heating completely. Young poultry, newborn livestock, and vulnerable animals may still require carefully controlled warmth, but thoughtful design can reduce energy use, lower costs, and make the farm less dependent on equipment. Why pay to create every degree of heat when sunlight, compost, and properly selected materials can provide part of the work naturally? Tip 5. Dual roof cavities and air draft ventilation. Winter requires protection from cold, but summer creates another serious risk: trapped heat, humidity, and stale air. Tip number 5 is dual roof cavities and air draft ventilation. A tightly enclosed barn or poultry house may seem secure, but without enough ventilation, it can quickly become dangerous. Summer heat combines with moisture from animal breathing, manure, spilled water, and wet bedding. The result is a hot, humid environment where ammonia, mold, pathogens, and respiratory problems can develop rapidly. Heat stress can reduce feed intake, milk production, egg production, fertility, growth, and overall animal performance. In severe conditions, it can become fatal. That is why a livestock building must be designed to breathe. Amish builders often encourage natural ventilation by using the stack effect. Warm air is lighter than cool air, so it rises toward the highest part of the building. Continuous ridge vents or wooden cupolas allow this hot, moist air to escape. At the same time, openings beneath the eaves allow cooler, drier air to enter at a lower level. As the warm air exits through the roof, fresh air is drawn inward and moves through the building without requiring an electric fan. For this system to work well, both the lower intake and upper exhaust openings must remain clear. Blocking the eaves while leaving only a ridge vent greatly reduces airflow. The building also needs enough open space around it for wind to reach the intake areas. Structures requiring greater temperature stability, such as ice houses or above-ground cold storage buildings, may use a dual-roof design. A second lightweight roof made from boards, slats, or metal panels is installed roughly 3 feet above the main weatherproof roof. The upper roof receives most of the direct solar radiation. Air moving through the open cavity carries away much of that heat before it reaches the lower roof. The inner roof remains shaded and noticeably cooler, reducing the amount of heat transferred into the building. This 3-foot space acts as a protective thermal buffer, much like a permanent shade canopy covering the entire structure. The same principle can be adapted to certain livestock shelters where extreme summer heat is a regular problem. Although roof strength, wind exposure, snow load, and local building requirements must always be considered. Tip 6. Thermal mass insulation and above-ground cold storage. Imagine stepping outside on a hot, humid afternoon in the middle of August. The grass is dry, the air feels heavy, yet inside a simple wooden building, you find cold milk, fresh butter, and even ice that has been stored since winter. This is tip number 6. Thermal mass insulation and above-ground cold storage. Long before electric refrigeration became common, Amish communities learned how to harvest winter cold and preserve it through the warmer months. Their solution was the double-walled ice house, or above-ground cold cellar. These buildings are constructed with a large cavity between the inner and outer walls, often measuring from 12 to 36 inches wide. That space is tightly packed with dry, affordable insulating materials such as sawdust, straw, or rice hulls. The goal is simple: slow the movement of outside heat into the cold interior. When ponds freeze deeply during winter, large blocks of ice are cut and transported to the ice house. The blocks are usually made as large and uniform as practical because a compact mass exposes less surface area to warm air and therefore melts more slowly. The ice is stacked closely, much like bricks in a wall, with as few open spaces as possible. Once the chamber is filled, the entire mass is covered with a thick layer of clean, dry sawdust. This extra insulation limits air movement and protects the ice from heat entering through the doors and walls. A natural pond is not the only way to produce ice. Some off-grid farmers build sturdy wooden forms lined with waterproof material, fill them with water during freezing weather, and allow the cold night air to form blocks gradually. The blocks can then be removed, stacked, and insulated inside the storage building. The principle behind the system is straightforward. Heat naturally moves from warmer areas toward colder ones. But dry sawdust, straw, and similar materials contain countless small air pockets that slow this transfer. The thicker and drier the insulation remains, the more effectively it protects the stored ice. Drainage beneath the ice is equally important. A gravel, stone, or properly sloped floor allows meltwater to escape instead of collecting around the blocks. Standing water speeds melting, encourages odors, and creates damp conditions that can damage the wooden structure. With thick insulation, limited air leakage, tightly stacked ice, and reliable drainage, a well-built ice house can preserve a large amount of winter ice far into summer. Tip 7. Octagonal pegged timber joinery. Step inside a timber frame barn that has stood for more than a century and look carefully at its massive posts, beams, and rafters. In many traditional structures, those heavy timbers are not held together by modern screws, steel brackets, or rows of nails. This is tip number 7, octagonal pegged timber joinery. Modern buildings often depend heavily on rigid metal fasteners. These fasteners are strong, convenient, and useful, but timber does not remain perfectly still throughout its life. Wood absorbs and releases moisture as humidity changes. It expands during damp weather and contracts as conditions become dry. When a joint repeatedly moves around a rigid fastener, the surrounding wood fibers can gradually loosen or become damaged. Over many seasons, poorly designed connections may begin to shift, squeak, sag, or pull apart. Traditional Amish builders address this movement by joining large timbers with carefully fitted mortise and tenon joints. One beam is shaped with a projecting tenon that fits into a matching mortise cut into the adjoining timber. The joint is then locked with a strong wooden peg, often shaped by hand from dense oak. The peg may be formed with 8 sides and driven into a round hole. As it enters, the edges of the octagonal peg press firmly against the surrounding wood, producing a tight mechanical grip. The peg must be properly sized and aligned so it locks the joint without splitting the beam. Because both the peg and the surrounding frame are made from wood, they react to changes in humidity in a more compatible way. During damp periods, the parts swell. As the frame seasons and dries, a well-fitted joint can remain tight rather than allowing excessive movement. Some traditional frames also use slightly offset peg holes, a technique that draws the tenon firmly into the mortise as the peg is driven. When executed by an experienced timber framer, the connection becomes strong while still allowing the structure a small amount of natural flexibility. That flexibility matters in large barns exposed to wind, vibration, shifting loads, and heavy snow. Instead of depending on one narrow metal fastener, the connection spreads forces across broad wooden surfaces within the joint. This method requires careful layout, sound timber, accurate cutting, and proper peg placement. It is not simply a matter of drilling a hole and driving in any piece of wood. When done correctly, however, mortise and tenon joinery creates a strong structural skeleton capable of serving several generations. Tip 8. Cross-buck bracing and triangulated wind braces. Anyone who has worked around livestock has probably struggled with a heavy gate or barn door that drags across the ground. As the outer corner drops, the hinges strain, the latch no longer lines up, and opening the door may require lifting its weight by hand. Tip number 8 solves this problem through cross-buck bracing and triangulated wind braces. Gravity constantly pulls downward on the unsupported outer edge of a gate or swinging door. The farther that edge sits from the hinges, the greater the leverage acting against the frame. Traditional Amish builders strengthen these openings with a crossbuck, an X-shaped arrangement of diagonal boards built directly into the gate or door. Rather than allowing the rectangular frame to twist, the diagonals transfer the load back toward the stronger hinge side. The bracing changes how the force travels through the structure. Some members work in compression, while others resist tension. Instead of leaving the outer corner unsupported, the weight is distributed along the diagonal members and directed toward the posts and hinges. This is why the position and direction of a brace matter. A poorly fitted decorative board may look correct, but provide little support. The diagonal members must connect firmly to the corners or structural rails, so the load can travel through the complete frame. The same principle is used on a much larger scale throughout the barn. A simple square or rectangle can rack sideways under wind pressure, gradually changing shape into a parallelogram. A triangle is far more resistant to this movement because its shape cannot change unless one of its sides changes length or one of its connections fails. By installing diagonal knee braces between posts, beams, rafters, and wall sections, Amish builders create a network of rigid triangles. These braces help prevent the frame from leaning, twisting, or shifting during strong winds. When a storm presses against one side of the barn, the bracing guides that lateral force through the frame and down toward the foundation. Instead of allowing one wall or connection to absorb the entire load, the structure shares the pressure across multiple members. For livestock facilities, proper bracing protects more than the building. A sagging gate can injure an animal, create an escape point, or fail when cattle push against it. A distorted barn frame can also damage doors, roofing, siding, feeding equipment, and partitions. Tip 9. Specialized rot-resistant native timber selection. Walk through a modern building supply store, and you will see large quantities of treated lumber designed to resist insects and decay. Traditional Amish builders often begin from a different direction. Instead of asking one type of wood to perform every task, they select species according to the job. This is tip number 9, specialized rot-resistant native timber selection. Every tree species has its own density, grain pattern, strength, weight, workability, and natural resistance to moisture. Experienced builders understand that timber performing well as interior siding may not be suitable for a structural post, while a strong framing wood may be unnecessarily heavy or difficult to use for exterior boards. For major structural components such as posts, beams, floor joists, and peg joints, oak is a traditional choice. It is dense, hard, and capable of carrying substantial loads when properly selected, dried, and sized. This strength is especially valuable in barns where loft floors may support large quantities of hay, feed, tools, or equipment. A sound oak frame resists crushing and bending, but the timber must be protected from prolonged moisture, because even durable wood can decay under consistently wet conditions. For skids, runners, exterior framing, and other areas facing greater moisture exposure, builders may choose hemlock or larch when those species are locally available and suitable. Their natural characteristics can provide better decay resistance than many ordinary softwoods, particularly when the wood is kept ventilated and separated from wet soil. No wood should be treated as completely immune to rot or insects. Proper drainage, airflow, roof overhangs, and ground isolation remain essential. Choosing a durable species helps, but good design is what allows that timber to reach its full service life. Eastern white pine is often used for upper siding because it is relatively light, workable with hand tools, and well suited to board and batten construction. Wide boards are installed vertically, while narrower battens cover the joints between them. This arrangement allows each board to expand and contract with seasonal changes without forcing the entire wall to buckle. Vertical installation also encourages rainwater to travel downward rather than remaining trapped along horizontal joints. Modern builders may combine these traditional principles with engineered siding products, including panels treated with preservatives such as zinc borate. These materials can offer consistent dimensions, long warranties, and a traditional exterior appearance when installed, according to the manufacturer's directions. The important lesson is not that one material is always superior to another. It is that every part of a farm building has different demands. Posts carry weight. Skids face moisture. Siding sheds rain. Interior boards must remain easy to clean and repair. A durable barn begins by matching each material to the conditions it will actually face. Selecting the right wood from the beginning is usually more effective than expecting chemicals or repairs to correct a poor choice later. Tip 10. Gravity-fed handling and multi-level flows. A working farm demands repeated lifting, carrying, pushing, and climbing. When those movements are performed every day for many years, the back, knees, shoulders, and hands eventually pay the price. Amish barns are designed not only to shelter livestock, but also to reduce unnecessary labor. This is tip number 10. Gravity-fed handling and multi-level flows. Many modern farms use tractors, conveyors, elevators, and powered augers to move hay, bedding, and feed. These machines are extremely useful, but traditional multi-level barns show how thoughtful design can allow gravity to perform part of the work. Hay and straw are commonly stored in a high loft directly above the livestock area. This keeps valuable forage dry, protects it from ground moisture, and positions it close to the stalls where it will eventually be used. Strategically placed floor openings or trapdoors allow hay and bedding to be moved downward without carrying every load through the building. When animals need feed or fresh bedding, the worker opens the appropriate hatch and lowers or drops the material into a manger, passageway, or stall below. This arrangement shortens travel distance and reduces the number of times heavy material must be lifted. It also keeps daily chores moving in a clear direction. Supplies enter and rise to storage, then travel downward as they are consumed. To move hay into the upper level, traditional barns may include a hay prow extending beyond the high gable. A pulley, trolley, rope, and overhead track work together to lift bundles from a wagon and carry them into the loft. The pulley system creates mechanical advantage, allowing people or horses to raise much heavier loads than they could lift directly. Once the hay reaches the correct height, the trolley carries it along the track so it can be released inside the storage area. A system like this must be built and maintained carefully. Ropes, pulleys, anchors, tracks, and lifting points should be inspected regularly, and no person or animal should stand beneath a suspended load. Barn doors follow the same labor-saving philosophy. Large swinging doors are difficult to control in strong winds and require clear space in front of the building. Sliding doors hang from wheeled hardware on an overhead rail, allowing even a heavy wooden panel to move with relatively little effort. Because the door travels parallel to the wall, it does not swing into livestock, equipment, or passing workers. When the track remains level, protected, and clean, a properly balanced door can be opened smoothly without placing unnecessary strain on the body. The deeper lesson is to design the farm around the natural movement of materials. Feed should travel toward the animals with as few turns and lifts as possible. Bedding should move from storage to stalls without repeated handling. Manure should leave through a separate, efficient route rather than crossing clean feed areas. Are we arranging our barns in ways that exhaust our bodies? Or are we using height, gravity, and good workflow to make daily livestock care easier? Tip 11. Retrofitting standard sheds into biosecure chicken coops. You do not need to build an enormous barn from the ground up to benefit from practical Amish design. A standard, affordable A-frame or Quaker-style utility shed can be converted into an efficient and well-organized asset for a small farm. This is tip number 11. Retrofitting standard sheds into biosecure chicken coops. For many poultry keepers, managing a backyard flock becomes a constant struggle with predators, wasted feed, dirty eggs, unpleasant odors, and daily cleaning. Amish-inspired layouts address these problems by clearly separating the human work area from the space occupied by the chickens. When you open the main door, you should not have to step directly into manure, bedding, and dust. Instead, the entrance leads into a clean, dry vestibule about 3 feet deep. This small service area provides a protected place for feed containers, egg cartons, medications, gloves, and clean tools. A sturdy partition made from plywood and welded wire separates the vestibule from the poultry area. This barrier allows you to observe the flock while preventing chickens from reaching stored feed or contaminating clean equipment. Nest boxes can be built directly into the partition. By giving the floor of each nest a gentle slope, newly laid eggs roll carefully toward a covered collection area inside the clean vestibule. This allows eggs to be gathered without entering the flock area and reduces the chance of eggs becoming dirty, broken, or eaten by the hens. A large gravity feeder can also be incorporated into the dividing wall. The upper storage compartment may hold more than 100 pounds of grain and automatically replenish the feeding trough as birds consume the feed. When properly sealed and raised away from damp bedding, this system keeps grain cleaner, reduces waste, and limits the number of times heavy feed bags must be carried into the coop. Predator protection must begin at the foundation. Raccoons can open weak latches. Foxes and coyotes can dig beneath walls, and smaller predators can squeeze through surprisingly narrow gaps. Raising the coop on a knee-high concrete block base creates a durable, lower barrier that is easier to clean and harder for animals to damage. Heavy welded hardware cloth should be secured around vulnerable openings and extended at least 12 inches below ground, or laid outward as a buried apron around the perimeter. Unlike ordinary chicken wire, strong hardware cloth is designed to resist tearing and prevent predators from reaching through. Inside the poultry area, a deep litter system can reduce cleaning labor when it is managed correctly. A base of dry pine shavings, often around 6 inches deep, absorbs moisture and provides carbon to mix with the manure. As the hens scratch, they naturally turn the upper layer and help distribute the droppings through the bedding. Fresh, dry material must be added whenever the surface becomes damp, compacted, or strongly scented. Good ventilation remains essential because deep litter should never be used to hide moisture or ammonia. Some keepers apply a very small amount of food-grade diatomaceous earth, but it must be handled carefully because airborne dust can irritate the lungs of both birds and people. When moisture, airflow, and bedding depth are properly controlled, the litter begins breaking down gradually. Instead of producing wet manure, strong odors, and clouds of flies, the system creates a drier mixture that can later be removed and finished in a compost pile before being applied to the garden. Keeping chickens should not require entering a dirty building several times each day. With a clean service area, protected nest boxes, gravity-fed storage, strong predator barriers, and properly managed bedding, the coop itself can reduce much of the feeding, cleaning, and egg collection work. Tip 12. Chalk line layouts and coordinated assembly. We have now reached the principle that brings all the traditional Amish building methods together. This is tip number 12. Chalk line layouts and coordinated assembly. How can a large group of people arrive at an empty building site in the morning and raise a massive multi-level barn before the day is over, without depending on computer screens, complicated communication equipment, or a stack of printed plans? The process begins long before the frame is lifted. The design is standardized, the work is carefully organized, and full-size chalk lines are snapped directly onto a flat wooden platform. These lines show the precise dimensions and angles of the structural frames, commonly known as bents. Instead of asking every worker to interpret a complex drawing, the master carpenter creates a physical template at full scale. Heavy green timbers are placed directly over the chalk marks, measured against the pattern, and cut to match the required shape. Mortises, tenons, brace locations, and peg holes can then be prepared while the frame remains flat on the ground. Each bent is assembled and checked before anyone attempts to raise it. In some cases, siding boards and other components are also prepared in advance, with fasteners started so they can be installed quickly once the structure is standing. Because similar barn designs are repeated from one farm to another, experienced community members already understand the basic sequence. They know where the corner braces belong, which beam connects to each post, and which wooden peg locks each joint. This shared knowledge prevents dozens of people from waiting for individual instructions. Every group has a defined task, and each stage is completed in the correct order. When the barn raising day begins, the site operates through careful cooperation. One team uses ropes and lifting poles to raise the heavy bents. Another connects them with horizontal beams and temporary braces. Other workers secure the wall framing, install siding, and prepare the roof. Younger helpers may organize tools, carry pegs, pass boards, and keep materials moving toward the workers who need them. Food, water, and rest are also coordinated so that the entire crew can continue working safely and efficiently. The speed comes not from rushing blindly, but from preparation, repetition, and trust. Components have already been measured. The structural sequence is understood. Materials are placed near the point where they will be used, and every person knows how their task supports the next one. By late afternoon, the sound of hammers begins to fade, and the dust settles around a tall, solid barn raised through skilled labor and community effort. It is a remarkable example of efficiency, but the deeper lesson extends far beyond construction. The most powerful resource on a farm is not always a tractor, crane, or hydraulic lift. Sometimes it is a group of neighbors who bring experience, strength, and a willingness to stand beside one another when the work is too large for one family to manage alone. Conclusion: reclaiming the wisdom of the plain path. As we look back at these 12 practical Amish building principles, it becomes clear that the lesson reaches far beyond timber, stone, roofs, and wooden pegs. The Amish do not build simply to follow the newest architectural trend or to impress people passing along the road. They build with the expectation that the same barn may still be sheltering cattle, storing hay, and serving another generation many decades from now. They imagine grandchildren standing beneath those beams, caring for the same land and wondering whose hands shaped the joints, raised the posts, and built every part with such patience. Their approach is also deeply connected to freedom. A small farm should not automatically become a source of overwhelming loans, endless utility costs, and expensive equipment that cannot function without fuel or electricity. When we use simple geometry, appropriate local materials, natural airflow, sunlight, gravity, and the support of other people, farm buildings become more than shelters. They become reliable working systems that protect animals, reduce labor, lower operating costs, and support a more self-sufficient way of life. These principles do not require copying every detail of an Amish barn. They ask us to look more carefully at our own land and make thoughtful decisions before we build. So take a moment to look across your garden, poultry yard, pasture, or livestock area. What is the first practical improvement you can make? Perhaps your next chicken coop can be positioned to receive more winter sunlight. Maybe an existing shed needs a properly compacted gravel pad, stronger diagonal bracing, or better ventilation. Perhaps the most important step is simply asking a neighbor to help with a project and offering your own help in return. Thank you for traveling this road with us today on Farmyard Care. When these ideas are useful to you, support the channel by pressing the like button, subscribing, and sharing in the comments which of the 12 building principles you plan to use first on your own property. Keep the design simple, keep the work honest, and whenever possible, let the land, gravity, airflow, and good planning carry more of the load. We will see you again soon.